Welcome to this recording. In this recording, we are going to look at linear programming, the graphical method, and then we're going to have one use case. In this use case, we are going to look at Backsavers company. So this company makes primarily two different models of backpacks for students, the collegiate and the mini. Both of these models are made from the same nylon fabrics, and the company receives a 5,000 square feet shipment of material each week. The collegiate requires 3 square feet, while the mini requires 2 square feet. The sales forecast indicates that at most 1,000 collegiate and 1,200 minis can be sold per week. And each collegiate requires 45 minutes of labor to produce, and it generates a profit of $32. Each mini requires 40 minutes of labor and generates unit profit of $24. The company has 35 laborers, and each provides 40 hours of labor per week. The management wishes to know what quantities of each of the backpacks to produce per week in order for them to maximize their profit. Here we are going to formulate the model algebraically using the 5 steps, and this kind of like the foundational steps we have to follow in linear programming, regardless of what use case or application that we are looking at. Then we use graphical method here to solve this model. This is because graphical method is only recommended when you have 2 decision variables. If you have more than that, it becomes very complicated because it's hard kind of like for students to start thinking beyond the 2-dimension, right? Then we are going to explain the results once we're done. So the approach here, the first step is to understand what the question is asking for, the type of the question that we have. So in this case, we have a maximize or linear programming model. And then step 2, this is when we define the decision variables. Since we have 2 different types of backpacks that we produce every week, let X1 be the number of collegiate backpacks produced per week, and X2 be number of mini backpacks produced per week. Then we look at objective function. We know $32 is the profit from number of backpacks produced, collegiate backpacks, and then $24 is the profit from each of the mini backpacks produced. So the profit equation is going to be 32x1 plus 24x2. Next, we are going to look at constraints that we have. In order for us to have a solution, all these constraints have to be met. So we have 3x1 plus 2x2 is less than 5,000, and that's for the material constraint. The labor constraint, we have 45x1 plus 40x2 is less than 84,000. Where 84,000 is coming from is 35 laborers times the number of hours, which is 40 hours per each laborer times 60, so that we have minutes. So the 84,000 is in minutes, right? Some people, they keep it in hours. That means you have to divide, for the labor constraint, you have to divide everything by 60. But avoid rounding off if you want to go to the small places. I think leave it as fractions. That way we don't round off earlier in the process. Then the sales constraint, we know you can sell up to 1,000 collegiates per week and up to 12,000 minis per week. Then the last step is the non-negativity constraint, where in this case, we are saying we have to produce each of these backpacks every week, at least one of each. That's why we have X1 and X2 greater than 0. The next, we are going to use the graphical method. In the graphical method, the first approach, the process is you pick one of the equation in those inequality, in those constraints, and then you plot it. In this case, we are going to use material constraint equation for demonstration purpose, which is 3x1 plus 2x2 is less than 5,000. The first step is to replace the inequality sign with an equal sign. And then you plot the line for this equation. The easier way is set x0, x1 to 0, and find x2, which is 2,500. And then set x2, 0, and find x1, which is the value we have here, and then we draw a line that covers that. And then next, that process is repeated for all the other inequalities that we have, all these equations that we have. Then next, after you plot each of the line that you plot, you have to indicate which region is needed. And the way we test that, you can pick one of the points on either side of the equation. It's easy always to pick 0, 0 and put it in the original equation. In this case, that's you put it in this this equation. So 3x 3 times 0 plus 2 times 0, we know the answer is 0, which is less than 5,000. That means the side where we pick that point is needed, and you shade that side, as you can see. You repeat this for all the other constraint equations, and then afterwards, you are going to have a common region that applies to all of them. So if you are to shade, let's say here, you would shade everything you have on this side, and then you end up having this orange section as the common one. Then once you have that, since this is a linear programming model, we don't have binary constraints. Those one we'll look at that later. That means any point within this region, orange region, is a possible solution, but does not necessarily mean it's the optimal solution. So to know which one is the optimal solution, we pick all these points at the corners, right? And put them in the equation, in the objective equation, and then see what value we get. So in this case, point B gives us the maximum profit. Hence, that's the solution for that. So in order for the company to make as much profit as it can, it has to make 1,000 corrigates and 975 minutes, which will give you the 55. That ends this use case. Thank you.